Okay, we are back. So, here is our goal with this video. Today means nothing, as a concept in general. Suppose that f from u to r is continuous, and that for every limit point p of u, the limit as x approaches p of f of x exists. So, suppose f is a continuous function, and wherever you might ask about the limit as x approaches p of f of x, that limit exists. Then there exists a continuous function, g, from u to r, the closure of u to r, extending f. So this is why sometimes when you have a function which has the property, so let's see, this is an aside. When f is not continuous at p, but the limit as x approaches p of f of x exists, f has a removable discontinuity at p. So that's just a bit of notation, because what does this theorem say? This theorem says that, well, this requires it at every limit point, but you could write this at a single limit point too. If you can take the limit as x approaches p of f of x, then you can find a new continuous function defined at that limit point, which extends f. And the picture of this is, well, exactly the picture you would think. Suppose you have a function which is discontinuous at a point, but for which the limit is defined. So what do you do if you want to define a new function which is continuous at that point, but is otherwise the same function? Well, you kill that, and you fill in that dot instead. That's basically what this theorem is saying, except maybe you have a function that is not only having one badness, maybe it has badness all over the place, but you can still take limits at all those points of badness. So, here's a corollary of that result. Suppose that f from u to r is uniformly continuous, and there exists a continuous function defined on the closure which extends that function f. So let's talk about why this is a corollary. So what do I know about uniformly continuous functions? Well, I know that if you have a uniformly continuous function, then that limit will be defined at every limit point of f. And as a reminder, the reason that what I just said is true is because of theorem 3.8.13. That's the thing to cite. So, let's go through the proof. Proof of corollary 3.9.10, assuming theorem 3.9.9. So notice we haven't proven theorem 3.9.9 yet, so we won't really be able to believe theorem 3.9.10 until we prove it. But let's go through the proof of corollary 3.9.10 to say maybe why we should care about 3.9.9. So let's suppose that f from u to r is a uniformly continuous function. Then in particular, and it might seem silly to say, f is continuous. Every uniformly continuous function is also continuous. And the reason that I'm pointing that out is because if I'm going to use theorem 3.9.9, I need to check that all of the hypotheses are satisfied. One of them is f is continuous, so I better say that f is continuous. Next, I need to point out that for every limit point p of u, the limit as x approaches p of f of x exists. Well, why is that true? Well, consider any limit point p of u. By theorem 3.8.13, as I just said, I have that the limit as x approaches p of f of x exists. Thus, all of the assumptions of theorem 3.9.9 are satisfied, and so we conclude that the conclusion of theorem 3.9.9 is satisfied. That is, there is a continuous function g from the closure of u to r, extending f. Neato. Now on to the proof of theorem 3.9.9. Let's do it. So let's read the theorem and see what we need to find. So let's suppose that f from u to r is continuous, and that for every limit point p of u, limit as x approaches p of f of x exists. I need to come up with a continuous function, because I need to show one exists, to find on the closure of U, which extends f. So, let's remember there are like two different types of points in U bar. U bar is U together with the set of all x's such that x is a limit point of U. Right? That's what I need. That's the set. So that means I need to come up with a function that's defined on U and on these points. Let's see, when x is in U, then g of x has to be f of x, right? Because g is supposed to extend f, so whenever x is in the domain of f, g of x has to be the same as f of x. So when x is in U, g of x has to be the same as f of x. So at every point p in U, well, I guess I'm calling it p instead of x, but that's okay, g of p must be the same as f of p. The only other type of point in U bar is a limit point of U. When x is a limit point of U, well, g of x needs to be the same thing as the limit, g of p, let's say p. And the reason to say p is because I want to take the limit as x approaches p. I don't want to make up a new variable name other than x for that. G of p should be the same thing as the limit as x approaches p of g of x. Now, I know for a fact that there are points in U, in the domain of f, which are really, really, really close to p. So I should get the same result if I take the limit as x approaches p of f of x instead. So I'll use that as the definition. So the only other type of point in U bar is a limit point of U. By continuity, then, the g of p should be the limit as x approaches p of g of x. Now there are limits, there are elements of U, which are very, very close to x. At elements of U, g of x has to be equal to f of x. Thus, the limit as x approaches p of g of x should be the same as the limit as x approaches p of f of x. So that gives me my definition for g of x. Here's the definition that I will use. For any point in U bar, g of p will be defined as f of p if p is in U bar. On the other hand, if p is a limit point of U bar, then g of p will be defined to be the limit as x approaches p of f of x. Nice. So I have this piecewise definition of g. I have one definition when p happens to be in U. I have another definition when p happens to be a limit point of U. So one thing you should be suspicious of whenever you see a piecewise definition, when the two pieces overlap, you need to worry, is it actually well defined? Do those two things give the same answer when p is both in U and is a limit point of U? Well, let's check that. If p is both in U and is a limit point of U, then these two things have to agree in order for g to even be a function. So let's just check that. Remember, f is continuous. So let's let p be a point in U, which is also a limit point of U. I need to have f of p equal to the limit as x approaches p of f of x. And if you think really quickly, just remembering some results we know about continuous functions, you'll see that, well, yeah, that's true. So maybe go back earlier in the notes and recall what theorem 3.1.5 says. Do that and then come back. Great, you did that. So, by theorem 3.1.5, f of p is equal to the limit as x approaches p of f of x as needed. Nice. So all that means right now is g is actually a function. The formula defining g actually defines a function. Now we have to check for continuity. So remember what continuity says. To prove a function is continuous, we need to prove that for all p in U bar, and for all epsilon greater than 0, there exists a delta greater than 0, such that for all x in U bar, if absolute value of x minus u, x minus p, is less than delta, then absolute value of g of x minus g of p is less than epsilon. And so I think I'll go ahead and sketch a proof off to the side, and then I'll come into the actual text of the proof. This will take longer, but I think it'll be worth it. If you want to watch it like 4x speed and then come back when I start filling in the actual proof, feel free to do that. In fact, if you feel like you already understand how the proof should go ahead and fill in the proof, and then come back and see if we wrote down the same proof. Alright, so this is just going to be a sketch. So let's maybe say this much, let p in u and epsilon be greater than 0. Well, I won't be able to declare delta explicitly. So maybe I'll just put in red get delta. And maybe I'll give myself some space for the things that I will need delta to satisfy. Then I'll get to let x be in u, and I'll get to assume absolute value of x minus p is less than delta. And let's see, there are like some cases, right? Oh, those shouldn't be u's. Alright, I have to assume that things inside are in u bar. There are some cases, right? I know what u bar is. U bar is u union with the set of all limit points of u. So there are going to be like 4 cases. There's when x and p are in u. There's the case that x is in u and p is a limit point of u. There's the case that x is a limit point of u, p is in u, and the case that x and p are both limit points. So, right, we're just going to sketch the proof first. So let's start with this first case. So my eventual goal, and I'll come up with a proof by thinking backwards. So I eventually want f of x, well, I want g of x minus g of p to be less than epsilon. There's my goal. Now wait, in this case 1, x and p are both in u. So my real goal, g of x is the same as f of x, is the absolute value of f of x minus f of p is less than epsilon. Okay, well that's nice, I guess. Oh wait, but f is continuous. So if I happen to know that absolute value of x minus p is less than some choice of delta, then the absolute value of f of x minus f of p is less than epsilon. Nice, so that's maybe not going to be all I'll need, but for case 1 anyway, I'll use the fact that there exists a delta bigger than 0, such that for all x and p in u, if the absolute value of x minus p is less than delta, then f of x minus f of p is less than epsilon. Alright, nice. So let's now go to, I don't know, case 2. I'm not sure if this is the same model. I'll do the cases in here. No, they aren't even the same names, but that's okay. I'm going to do this case second. X is a limit point and p is an element of u. So I'll follow the same pattern. Right, this is all just scratch walk. So here's my goal. my goal is absolute g of x minus g of p is less than epsilon. Now, let's see what I have. X is a limit point of u, and p is in u. So I know what g of x is. G of x is the limit as some other variable y approaches x of f of y. And g of p, well, that's the same thing as f of p. So there's my new goal. Well, let's see. Let's look at what this is. Let's call that quantity, I don't know, L. It's also called g of x. Yeah, it's called g of x. Let's just call it g of x. So let's look at that. So since g of x is the limit as y approaches x of f of y, what does that tell me? That tells me that there exists some choice delta prime such that if absolute value of y minus x is less than delta prime, and y is in U, the domain of f, then absolute value of f of y minus g of x is less than something that's as small as I could possibly want. For now, I'll put an epsilon there and I'll see if it's good enough. Oh, cool. So let's see what that says. That says that I can get f of y to be close to g of x. I eventually want g of x to be close to g of p. So if I can also get f of y to be close to f of p, I'll be happy. So let's try to do that. So right now, so let's take absolute value of y minus x less than delta prime, and absolute value of y minus x less than, I don't know, delta. Then, what will I have? I'll have absolute value of y minus p less than or equal to absolute value of y minus x plus the absolute value of x minus p, right, the triangle inequality, less than delta plus delta, which is 2 delta, which isn't what I want, but that tells me what I need to fix. So, looks like I need to take that delta and divide it by 2. So let's see what I would get in that circumstance. So once I have absolute value y minus p less than delta, I will be able to use continuity of f to get f of y minus f of p less than epsilon. Well, once I get f of y minus f of p less than epsilon, well, what will I be able to do? Well, I'll be able to use this, right? So I'll be able to use this to say, well, that means that the absolute value, remember the goal, there's the goal, g of x minus g of p equals g of x minus f of p equals g of x. And I found something that's simultaneously close to both. F of y is close to g of x, and f of y is close to f of p. So I'll add and subtract that. And now let's just gather these together. F of y minus f of p in absolute value, that's less than epsilon. G of x minus f of y, that's less than epsilon. So this is less than epsilon plus epsilon, that's no good, but I just need to divide them by 2. So I'll need to divide lots of things by 2. And let's see, this one just came from the statement of the limit. This one, however, came from the continuity of f. So this, I'll need to revise the choice of delta. Get where I'm going with this? Cool. So, I think that's enough just... No, this time. Let's write down all of the constraints that we'll need. So, case 3. We have x is in u, and p is the limit, is a limit point of u. Well, again, let's use the same tack to get this sketch. So the eventual goal is the same as it is in all of the other ones, is absolute value g of x minus g of p to be less than epsilon. And this time I have p as a limit point of u, so p, g of p rather, is equal to the limit as y approaches p of g of y. G of x, on the other hand, is the same thing as f of x. So eventually I want g of p to be close to g of x by taking x to be close enough to p. Well, if I take y close enough to p, what does this one mean? This bit means that there exists some delta prime such that if absolute, well, maybe 0 is less than absolute value of y minus p is less than delta prime, then the absolute value of f of y minus, the color changed, g of p is less than epsilon. Oh, so wait, let's check it out. Well, certainly that says whenever we take an input in u that is close to p, then the output will be close to g of p. Well, that's exactly the situation that we're in over here, right? There's an input in u. So let's just take absolute value of x minus p less than delta prime. Then, by exactly this, I'll get absolute value of g of x, f of x, minus g of p, less than epsilon. Not quite. There will be like a stupid case, right, because I'll need a 0 is less than there. But if 0 is equal to the absolute value of x minus p, then x is equal to p, so g of x is actually equal to g of p. So I'll just put that there so that I remember to come back to that. So the final case, so actually that gives me, it looks like there's what I need. If p is a limit point, then use the limit as y approaches p of f of y equal to g of p to get our choice of delta. Alright, I definitely didn't give myself enough space in that scratch bit then. That's okay, because the goal will be, once we've explored all of these ideas, we'll be able to write down the actual proof. Not quickly, but easily. This video might be a bit long. So let's do that last case. X and p are both limit points. Well, maybe I'll draw a picture. So what's the eventual goal? Is eventually that g of x to g of p is less than epsilon. That's what we want. And right now I know that g of x is the limit as y approaches p of f of y. So this will be true if absolute value of y minus x is less than delta. I guess I need to have one of those. I know, similarly, I'll know that if, I won't use y, but maybe I'll use z, f of z, that distance will be small. If 0 is less than absolute value of z minus p is less than some delta that we'll get to pick. Well, wait, now I can use, hopefully, continuity of f to say that these two things can be close. If y minus z are close enough. So let's look at that. So apparently I want y minus z to be close. Well, I think I can pull that off. There's y. There's z. I want this distance to be less than some small delta. Well, what do I know? I'm going to use this color green. I know that y is close to x. I know that z is close to p, and I get to assume that x is close to p. Nice. So, let's see what it looks like we'll need. In order to get this to be less than epsilon, this will need to be an epsilon over 3. This will be an epsilon over 3. This will be an epsilon over 3. In order to get this, I think I'll need all of those legs to be a delta over 3, delta over 3, delta over 3. And there's the idea of how this argument will go. Nice. So now let's put pen to paper and actually do it. So there are two cases. Either P is in U, or P is a limit point of U. And maybe for emphasis, if P is in U, we're already done. So we may as well assume here that P is also not in U. So let's do it in case 1. Let's suppose that P is in U, so that G of P is the same thing as F of P. Since f is continuous at p, there exists some delta bigger than 0, such that for all x in u, if the absolute value of x minus p then the absolute is less than delta, then the absolute value of f of x minus f of p, well, looking out to back to our scratch walk, looks like we need an epsilon over 2. Now we'll consider any x in u bar, and we will assume that the absolute value of x minus p is less than delta over 2. Now there are two cases in this one big case. Either x is in u, or x is a limit point of u. In case 1a, well, we suppose that x is in u. It follows then that g of x is equal to f of x. So the absolute value of g of x minus g of p is f of x minus f of p. Absolute value pairs are important, though, by the definition of g. It follows, though, that this is less than epsilon over 2, since the absolute value of x minus p, by assumption right now, is less than delta over 2 is less than delta. Great. So that completes the proof in the easiest of the cases. Let's do it in the harder of the two easy cases. Let's now suppose that x is a limit point of view. It follows then that g of x is equal to the limit as x approaches p. Nope, I can't. As y approaches x of f of y. Now, let's see what we needed. it looks like we needed this difference to be less than epsilon over 2. Since epsilon over 2 is bigger than 0, there exists something that in the scratchwork I call delta 1, but in the scratchwork I'm never in the exact same mindset as when I'm doing my actual typing of notes. So there's some delta prime, I'll call it delta 1, such that for all y and u, if the absolute value, if 0 is less than the absolute value of x minus y is less than delta 1, then the absolute value of f of y minus g of x is less than whatever positive number you want. All right, since this is a positive number, I can put that positive number there. All right, so let's keep it going. So how did the argument proceed? Let's see, I found some y value so that simultaneously the distance between y and x is less than delta prime and the distance between y and x is less than delta. Then I concluded that the difference between y and p was less than delta. So let's do that. Let's just state that choice of y. It's not part of the conclusion, but apparently it's part of the proof. Because x is the limit point of y, there exists some y in u such that simultaneously x minus y is less than delta over 2 and less than delta 1. So first let's control the difference between f of y and g of x. Well, apparently, as soon as we know absolute value of x minus y is less than delta 1, then f of y minus g of x will be less than epsilon over 2. Do we have absolute value of x minus y less than delta 1? We sure do, because of this. Since 0 is less than the absolute value of x minus y is less than delta 1, we see that the absolute value of f of y minus g of x is less than this. Epsilon over 2. Similarly, so the next step over here in the notes was to analyze the difference between y and p. So let's do that. Since the absolute value of x minus y is less than delta over 2, and the absolute value of x minus p is also less than delta over 2, this is why we needed the delta over 2, right? It follows that the absolute value of y minus p is less than or equal to the absolute value of y minus x plus the absolute value of x minus p by the triangle inequality is less than delta over 2 plus delta over 2 is delta. Cool. So by the continuity of f at p, right, f is continuous at p, as soon as I know the absolute value of f of y minus f of p is less, as soon as I know that the absolute value of y minus p is less than delta, I'll know that the absolute value of f of y minus f of p is less than epsilon over 2. Since g of p is equal to f of p, and since we know that absolute value of f of y minus g of x is less than epsilon over 2, I know there's a line right there, but I'll put it there instead. And we now know that the absolute value of f of y minus f of p is less than epsilon over 2. We can now finally analyze the difference between g of x minus g of p. So that is equal to g of x. And I know right now that f of y is the thing that's simultaneously close to everything. So I'll add and subtract f of y, or subtract and add, minus f of y plus f of y minus g of p is less than or equal to absolute value of g of x minus f of y plus absolute value of f of y minus g of p. That's less than epsilon over 2 plus epsilon over 2 is equal to epsilon. Hooray! Which is exactly as we required. So that completes the proof in, well, I guess that's case 1, the case that p happens to already be in u. So maybe I'll put a summary right here. Thus, g is continuous at P whenever P happens to be in U. So, the case left to deal with is, let's suppose that that point U isn't actually in U bar. Let's suppose that P is a limit point of U. In that case, I have that G of P is equal to the limit as X, Y. Y? Yeah, Y approaches P of G of Y. So, by the very definition of limits, there exists some delta 1 such that for all y in U, if the absolute 0 is less than the absolute value of y minus p is less than delta 1, then the absolute value of g of p minus f of y is less than, well, I think we came up with epsilon over 3 being what we need. But maybe in case you don't quite believe that that's what we need, I'll do it in a color that will remind me to be suspicious. Next, we'll consider any x in U, and we will assume that the absolute value of x minus p is less than that delta 1 divided by 3. Nice. So, there's the setup. So, let's think about case 2, subcase A. Let's suppose that x happens to be in U. Well, there's a small oversight in the notes, so let's see. So if I knew that absolute value of x minus p were less than delta 1 and that difference were bigger than 0, then I could get the conclusion absolute value of g of p minus f of x is less than epsilon over 3, which is what I would need. So let's add a few corrections, and these corrections will appear. So let's suppose x is not equal to p. Well then, since 0 is less than absolute value of x minus p is less than delta 1 over 3, which is less than delta 1, we conclude that the absolute value of g of p minus f of x is less than epsilon over 3, which in turn is less than epsilon, as we need. Well, almost as we need, right? I want a g of x to be there, but g of x is equal to f of x. Thus, the absolute value of g of x minus f of x is less than epsilon as needed. But since we added an assumption, we need an extra case. If x is equal to p, then I'll need to change things up a little bit. Then absolute value of g of x minus g of p, well, g is actually well defined, is equal to 0, which is less than epsilon, since epsilon is greater than 0. So there is that silly, trivial case, but you need to deal with it. Case 2b, let's suppose also that x is a limit point of U, so that in this case g of x is the limit as y approaches x of f of y. So there exists some delta 2, right? It can't be the same as delta 1, because delta 1 came from this limiting statement at p, not at x, such that if 0 is less than the absolute value of x minus y is less than delta 2, then the absolute value of g of x minus f of y is less than an arbitrarily small thing, but according to the scratch walk off to the side, apparently we wanted to divide things by 3. Since x is a limit point of U, there exists some y in U such that 0 is less than the absolute value of x minus y is less than some arbitrarily small error. And according to the stuff off to the side, it looked like maybe taking the min between delta 1 over 3 and delta 2 might be what we need. Well, let's see if this actually works. We'll be prepared to revise those two blanks. Since 0 is less than the absolute value of x minus y is less than delta 2, it follows then that the absolute value of g of x minus f of y is less than epsilon over 3, and that is by this implication. If the absolute value of x minus y is less than delta 2, then the absolute value of g of x minus f of y is less than epsilon over 3. So I know that the hypothesis of that if then holds, so the conclusion must hold. And notice, epsilon over 3, no, let's just leave that. Epsilon over 3 is epsilon over 3. Now, right, we're still not done. That wasn't our goal. Let's just remember the goal. This isn't part of the proof, so, but it's good to remember what we're aiming for. What we eventually need is absolute value of g of x minus g of p less than epsilon. Right now I have g of x being close to f of y. If I can get f of y to be close to g of p, then I'll be happy. So let's see why that should be true. So I want to get y to be close to p so that f of y is close to g of p. So let's do that. Since I know that the absolute value of x minus y is less than delta 1 over 3, and since I know there are some typos here, they are fixed in the version that you're looking at online right now, and I also know, well, I assumed at the beginning of the proof that the absolute value of x minus p is less than delta 1 over 3, I conclude that, well, let's see, x is close to y and x is close to p, so y must be close to p. So it follows then that y minus p in absolute value by the triangle inequality is less than or equal to that plus that, strictly less than delta 1 over 3 plus delta 1 over 3, also known as 2 delta 1 over 3. Now if I happen to know that y is not equal to p, then I'll have 0 is less than the absolute value of y minus p is less than, well, that's less than delta 1. Absolute value of y minus p is less than delta 1, so that since p happens to be in u, I can use the fact that the limit as y approaches p of f of y is equal to g of p to conclude that the absolute value of g of p minus g of y is less than epsilon over 3. Okay, so now, well, maybe I'll add an interjection right here, and this is added in your notes. If y happens to be equal to p, then, well, the absolute value of g of y minus g of p minus f of y, well, that's equal to, well, y is in u, so that means p is in u, is equal to the absolute value of f of p minus f of u equals 0, still less than epsilon. So we're still less than epsilon over 3, in fact. So we still get the desired result. Thus, as absolute value of g of p minus f of y is less than epsilon over 3, and the absolute value of g of x minus f of y is less than epsilon over 3, we can use the triangle inequality in the exact same way as we have dozens of times to conclude that, well, shoot, let's actually do it. The absolute value of g of x minus g of p is equal to the absolute value of g of x. F of y is the thing they found that was close to both of them. So by the triangle inequality, that difference is less than the absolute value of g of x minus g of y plus the absolute value of f of y minus g of p is less than epsilon over 3 plus epsilon over 3. Oh, it looks like I didn't actually have to divide anything by 3. So it looks like epsilon over 2 would have been just fine, but epsilon over 3 still works. So between 2 and 4 cases, depending on how you count them, we see that for all p in u bar and for all epsilon bigger than 0, there exists some delta bigger than 0. That delta depended on our choice of p, right? In fact, we had different ideas of how to get the p depending on whether or not p was in u bar. such that for all x in u bar, if the absolute value of x minus p is less than delta, then the absolute value of g of x minus g of p is less than epsilon. Thus, g from u bar to r is continuous, completing the proof. Great. So that was a long lecture. I hope it was worth sticking through it. I'll talk to you in a little bit. No. I want to point something out. So there's some things in the homework worth mentioning. Okay, so this PDF isn't the current one. So if you look at the version of the homework that is actually on the webpage, you'll notice some of them decorated with red, saying that in order to understand those, you have to have done stuff about compact sets. Only do those if you've done the stuff about compact sets. Those won't be one of amongst the problems that I'll grade, that I'll collect through Canvas. You should still do them. If you have done the stuff about compact sets, then I will allow you to do those for some amount of bonus something. Maybe upload them to the extra credit section and let me know what they are. Cool. Talk to you soon. Ciao.